Hello everybody. Hope you guys are doing well. Um, so yeah, continuing on our journey. Today we would try to understand a little bit about algorithms and when to use recursion and uh, another um, another algorithms, and then we'll say what is recursion, what is it, like why to use recursion, and then we will go on from there. Just let me check if the stream is up and running. So let's go back to Twitch. Okay. So the stream is visible. Let me go to stream manager. Okay, so uh, previously we studied about time complexities, right? Um, what is time complexity? And we saw like different time complexities, right? For example, often then uh, we saw log two base, and so basically whenever we are dealing with time complexity, we would be talking about worst case possible complexity, right? So we always talk about um, worst case complexity. Basically, that is denoted by O of n, right? So these are basically uh, asymptotic notations. Basically, asymptote is basically like it's like a mathematical graph, right? So we will be always talking about worst case complexity, that is denoted by O of n, right? So these are basically so when we deal with complexities, basically we say how is the algorithm performing when the input is high, right? When n is tending towards infinity. This is basically what we say in asymptotic um analysis, right? We say that n has to tend towards infinity, right? Uh, so okay, now there is a, so how to check if it's a, how to check if you have written the best possible code, right? Because in any code, right, I mean, for example, any function you define, it's not possible to run all the lines, right? You will be using some conditionals or some control flow, something, right? Because of which not all statements. So for example, if I have a piece of code, right? So suppose if I have read, this is my suppose this is 50 lines of code, right? um so this is say this is 50 lines, right? Now at a time you won't be able to run all of the lines, right? um I like all lines in this block will not run in one single flow, right? Because we may have some conditionals as well. We may branch out, and uh, some statements might not be executed. So how to define that we have written the best possible time complexity, like we have written the best possible code, is basically we do something called as asymptotic analysis, right? Now the not all pieces of lines require or are going to use up time, right? So basically we are going to deal with atomic operations, right? So we say how many times are the atomic operations being performed. This is what is going to define the complexity. Now before we go ahead, there is something called, now the two major blocks, or the two major issues will be when we are dealing with conditional flow, right? So in, so what all comes under conditional flow, right? So conditional flow includes loops. So when we say so basically not conditional flow, so basically we need to understand what control flow is, right? Now control flow, the main objective of using control flow is basically we are going to decide um, the next, like in the next what is the next operation that we are going to perform. So that is how we define control flow, right? So control flow basically defines the next operation to be performed, and there are various ways in which you can do control flow, right? So for example, if you have control flow, there are various ways. So first is basically you can achieve control flow using loops, right? Now loops again can be there are different types of loops, right? For example, you have a while, you have a do while, and you have for. So basically in this, like we the next operation to be executed is made by by small uh, conditions, right? For example, in each uh, we have a condition that we are going to be defined, and then we are going to increment it or decrement it, right? Same, the other way to achieve control is again when you use conditionals like if else. This is again basically going to define what next thing are we going to execute, right? The other way to how to decide our control flow is basically something called as using functions, right? So basically uh, so how this is going to happen is we are going to call the functions and then decide what is going to be executed. One more way to achieve control flow is basically by using recursion, right? Now what recursion does, so now recursion is a bit different, right? So you achieve what next is going to be or what next operation is going to be executed based on the call, right? Based on the recursive call that we make. So what function are we making is that recursive call is what is going to define the next thing that is going to be executed, right? So this is one way to achieve control flow. Now how to how do we calculate time complexity? So basically if we say what is recursion, so recursion is basically nothing but um, uh, this is basically control flow. Right now how it is achieved is by calling a function, when a function calls another function, right? So we say when a function calls another function, we say we are doing a recursive calling, right? Now there are different ways how you can um, calculate the time complexity, right? So for a recursive function, the method to decide time, there are different methods. Like first is basically you can use a recurrence relation, right? So basically like you are going to define the recurrence relation, or you can use master's theorem, right? So this is more, master's theorem is more theoretical. uh, Recurrence relation is what we are going to deal with, right? For example, now what does this recurrence relation define, right? So recurrence, uh, when you say recurrence uh, equation, right, what does it define? Basically it defines uh, amount of work done, and um and how the work is done, right? Let's see a little bit more about recurrence relation. Now, so basically, what we are going to define is basically a relation, right? A recurrence relation is basically a mathematical expression that expresses time complexity of a recursive algorithm in terms of so whenever in terms of it's some problem, right? Basically, it's a relation that is going to have the sub problem that is going to define the sub problem in terms of time, right? Now, one for example, the general form of a relation is basically this. This is my function of time, right? So this is the equation. This is like a very generalized form of the recurrence relation, right? Basically, A indicates the number of recursive calls. So uh, the recursive call that we're making. Now n by b is basically the sub problem that we are dealing with, right? And c is basically the constant, right? So this is basically a constant. I mean, this is not going to contribute uh, towards our complexity, right? It's just the number of recursive calls we make, and then the size of each sub problem, right? For example, let's define a for example, we have a factorial recursive function, right? So let's say so for example, this is a function, right? And then inside that I have an condition here. This is my base condition, right? There is one caveat or one silver lining is basically is whenever you're dealing with recurrence relation or whenever you're dealing recurrence, make sure that you have a base case ready, right? Because we don't want the stack to grow infinitely, right? And then we are going to do return. So this is where I'm going to call this function again, right? So now if you see what is going the way this function is going to work is uh, so this is the base condition, right? So this is where my function is going to stop, or base condition. So this is considered as the base condition. Now this is what is going to be defined in my recurrence relation, right? So how many sub problems am I going to is basically n minus one sub problems, right? And how much is the work done by each sub problem? So each sub problem is basically going to do unit amount of work, right? Or constant work. This is the work that is defined. So then my recurrence relation will be as you can write the recurrence relation as t of n minus 1 plus o of n. So this is basically for the constant work done. This is not going to come in our complexity, right? This is the major contributor towards our complexity, right? So the time complexity of this relation is going to be O of n. Now, for example, let's define another function, right? For example, if I have a Fibonacci, so I say this is Fibonacci of n, and then I say if n is less than equal to 1, then I'm going to return something. And then else, if that is not the return, then I'm going to make a call to P of n minus 1. So the way Fibonacci series is, so the first term is 1, the second term is going to be actually it starts from 0, so it's 0 1. The second term is the second term is considered as the okay, the third term is going to be the addition of the last two terms, right? So um for example, if I do a Fibonacci of 2, right? So Fibonacci of 2 will be Fibonacci. So the will be Fibonacci of 1 plus Fibonacci. So the uh, the way the first two terms are fixed. The third is the sum of the first two terms, right? So it is going to be uh, yeah. So the second uh, term is going to be the sum of the previous two, right? So then if we say the sum of previous two, then yeah. So the second term is going to be 0 plus 1, right? So when we do 0 plus 1, so this is equal to 1, right? Now if you go to the third term is going to be the sum of the previous two, right? So it is going to be 1 plus 1, which is going to be 2, right? So this is how the the Fibonacci series is getting generated, right? And from there is how we have got this relation, right? So now if you want to define the relation, so relation is going to be t of n minus 1 plus t of n minus 2, and each is going to do a unit amount of work, right? So the way um, uh, so now the way the complexity is going to be happening is like the way the growth of the function is going to happen is um so it is going to be because this t of n minus 1 is going to contribute to of n, right? No, but the other way we can define is also check how the tree is growing, right? So the okay, so the way it is going to happen is for each I'm going to do two successive recursive calls, right? Like for each function I need two calls. So then the complexity comes to our 2 power. The best way to analyze recursive is basically to check how the tree is growing. So for example, let's see, let's draw a Fibonacci of 5. This is going to, so when I do a Fibonacci of 5, so for each I'm going to make a previous two calls, right? So I'm going to call 4 and 3. Again for 4 I need to make to the calls to the previous two, right? So previous two is basically going to be my 3 and 2, and then again for 3 I'm going to make two more calls. So 3 I need 2 and 1, right? So remember this is the uh, base condition, right? So one is I have at the base, And then for 3 I'm going to make 2 more calls. So this is 2 and 1. This is going to be 0 and 1. So at each level I'm making, how many calls am I making? So if I, so for the first, okay, for the first thing I made 2. For the first is I made 2 calls, which is this. If I go further, again, so for this I have made 1, 2, 4 calls. Okay, so this is going to be 4 calls. And then if I go bottom, I'm going to make 1, 2, 3, 4, 5, 6, 7, 8 calls. So this is basically 8 calls, right? This is 8. This is this is 4. This is 2. So we can generalize this, right? The way the function tree is going to grow is 2 and then 4 and then 8. So you can say the growth of the function is 2 power n times, right? Okay. I mean, it's better, it's more easier to analyze the to analyze the recursive using the tree method, right, than to use the recurrence relation, right? For example, if it's even in case of n factorial, right? So for example, I'm doing, say, factorial of 5, right? If I make a factorial of 5, then I'm going to call 4 and then I'm going to call, this is, so I need 4 and, no, it's going to be 5 and 1 call to 4, right? Then if I go bottom, for if I'm going to call for 4, I'm going to make a call to 3 and 4, right? If I go another one, if I go further down, this is going to be 3 and 2. If I go one more level down, this is going to be 2 and 1. So this is the base condition, right? So what is happening? How is the tree growing? Uh, how can I check how the tree is growing? I'm just making single, right? Uh, so how is the function growing? So how many number of calls have I made? For example, to reach, oh, I can say, so to calculate phi, how many calls did I make? So this is the first. Okay, this is the first call. This is second. This is third. Oh no, wait. So here is my first for 5. So this is the first call, right? I make a call to 4, then I make a call to 3, I make a call to 2, I make a call to 1. So with input, how is my size going? And then from 1, I'm going to make a call to 0, right? So this is 1 and 0. This is going to be my last. So you can say this way, when the input n was 5, the number of recursive calls I made also was 5. So can't I say that this this recursive stack is going to grow linearly with the number of uh, calls, right? So hence this is going to be a complexity of O of n. Okay, but let's come back over here. Where we Let's come back to 100 and let's move. So to calculate the complexity of phi, I had to make how many calls? Uh, this is 5, right? So I'm going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 15. So at each level I'm making two calls. We can see that like the growth is two-way, right? So here for each I'm going to make two calls, right? So yeah, in that it was very obvious, right? But in Fibonacci, if we say for one I had to make two recursive calls. Oh, I see. So like I mean at each level I had to make two power calls, right? Like from here I went, but then here there was a linear transition, right? I just need to make one call at each level. Okay, let's see little bit more example of uh, let's see if it's let's see how the log 2 base and complexities, right? How to understand that. For example, if I have a binary search, right? The no recurrent. Let's see the okay. So let's say like log 2 base end, right? And then okay. So for example, I have an yeah. So this is my array, right? This is 1 3 7. So when I come the first call, what I'm going to do is I'm going to divide it, right? So I'm going to make half of this and then I'm going to search in one half after that half, and then I'm going to check like in which so at this level I'm going to check, right, on which side should I follow. Should I go on the right, or should I make the call on the left? And again, so what are we doing is at each level we are going to we are just ignoring half of the input, right? So hence you get that log 2 Bayesian criteria, right? So remember log 2 Bayesian is basically, so yeah, let's study powers of 2, right? So 2 power 1 is 1, 2 power 2 is 4, 2 power 3 is 8, and 2 power 4 is 16, right? So whenever you give log 2, so what value you are going to get is 1. Similarly, when it is log 2 to the power of 2, it is going to be 2. When it is log 2 to the power, it is 3. So like we are almost halving the input size, right? That is the whole idea behind that log 2 Bayesian, right? Because if my Oh, so that shrinkage is okay, I guess. So what are we going to do is yeah, I understand here. So if I go log 2 to the base 16 is going to be 4, right? So the way this is going to work is so if on initially I have the input size being 16, right? I'm not going to check on the entire 16. Instead I'm going to half it into, I'm going to check on either one of the half, either on the left half or either on the right half of 16, right? For example 16, yeah. So I okay, this is the halving, right? So if you see on the, if you have an element, you have 16 elements, right? We are not going to check all the 16 at once. So whenever I'm come here, what I'm going to do is I'm going to check on only on the half size of the input. And again, when I am checking for this, again I'm going to only check for four of elements. And when I'm for four, I'm going to check for two. And when I'm two, I'm going to check only one element. So basically, that is how that input is going to half by we are going to shrink the input size, right? So there is halving of that input size that happens. So basically, it divides how many times can I divide n by 2 till I get to 1. Like how many times? For example, in print, how many times should I divide this to get to 1? So I need to break down this into 8, right? So that is that halving action, that is because if I do log of 16, right, I'm going to get 4 over here, right? So total steps is going to be I need to, in order to reach 1 from 16. So if I'm at 16, and if I am at 16, if I'm halving this every time, so this is going to be 8, 8 is going to be 4, this is going to be 2, and this is going to be 1. So how many times? So this is first, second, so I need to do it 4 times to get to 1, right? So this is how the halving is, or the half action is taking place, right? Basically it indicates how many times I have to half the input size to get to 1 is what that halving action is indicating. Hence we say log 2 to the base n. Now this is a very critical, it's a very uh, or even if you see it like the tree method, so whenever I am at the tree, right, um I'm going to ignore one half at every time. Like either I may go on the right, or sorry, on the left, or either I may go on the right. I mean, I'm not going to make the, I'm not going to simultaneously check here and check here as well. So on either halves I'm going to do. For example, at 2 power n, right? For example, I was doing for 5, right? For 5, every time I need to check for the previous two, right? For example, if this is so for example the Fibonacci series, I need to check for if it's for 5, then I need to check for 4 and 3, right? So at each level I'm going to be checking two things. So as I further go down, similarly for 4, again I'm going to break this into previous two, right? Previous two is going to be 3 2, and again I'm, so the more break I do, I'm going to be doing is uh yeah, we are going to check for, like we need to do for both. So again, so here also I need to do the call, right? Like to get the final solution at this level, I need the results from both of these two, right? So it is going to be 2 and 1. 1 is the base, right? So now I'm going to make 4 calls. So if you see, the more I go down, I'm going to make power calls and make calls in the power of 2 power n. So hence it is said to be 2 power n. Um, whereas here if you see, for each call I'm halving the input size, and for O of n, it's if it's the factorial one, so 5. This is a very straight relation, right? I make call to 4, 4 makes call. So for each level, I'm going to make only one call. So total number of calls is equal to the total number of input size, right? But then here is not the case. So if you see in this, where is that? Where is that? Where is for? Yeah. So here, if the n is 5, then if you count the total number of calls, it will be uh, 2 power that calls, right? Approximately. So for example, this is again I'm going to make here 8 calls. So how many calls have I made? Is what? Just to calculate the Fibonacci of 5, I need to make this is 12, and so I'm making 20 calls. So to calculate the power of 5, I need to make uh, so if this is my input, right? If n is 5, so how many calls I had to make is the approximate. It is not exactly, but it comes to approximately. How much is uh, yeah, it is not exact, it's an approximate, but okay. So n is 5, that means so if I'm calculating Fibonacci of 4, then how many calls am I making? Oh, so if I call 1, 2, 4, 5, 6, 8. Uh, am I counting all of them, or am I leaving out some calls? Yeah, it is not exactly 2 power n, it is approximately growing by that rate. Then if it is, suppose if I need to make 3 power n, I guess he's saying for fun call we need two things to execute, right? Also he's saying okay, yeah, I guess what he's trying to say. So if you see, okay, so this level had only one node. Now when I went to this, I have two nodes now. So when I go deeper, I'm going more number of nodes. You have to remember in in a tree, the number of the nodes are basically representing the recursion calls, right? How much? Oh, I see. So now if I, it's a say if I have a so if I want 3 power n, so first call is going to be say like I'm calculating for 9. Suppose no, suppose I'm calculating for the recurrence call is as this way, like plus 2 plus 3. So if it's 5, so then I need to make a call to 4, uh, 3 and 2, right? So this is from one node. I have jumped to 3 nodes now. Okay, now for 4 again, I need to make a call. How many? This is again, this is going to be 3, 2, 1, right? 1 is the base. Again for 3, so 0 is the base. So this is going to be again, this is 2, 1, 0. Base has reached. We have reached the base. Again for 2. So I need previous 3, right? So previous 3 is, this is going to be minus 1. 0 and 1, right? So now at this level, if you compare from the previous level, how many nodes are we having? 1, 2, 3, 4, 5, 6, 7, 8. This is approximate. So this is 9, this is 6, this is, so this is 3, right? So if you generalize it, it will be 3 power n nodes at each level, right? But for my linear, it was only one node for one call. So and we generalized it to 1. Oh, I see. Let's let's do more. Uh, Diagram for recursive. Factorial is linear. Binary is, so binary. What is going to happen is, so if this is my say this was 7, right? And then although we have two, but we do not go to both of them. Either we go to the left or either we go to the right. So let's see about uh, let's see about merge sort, right? Even merge sort as well we are, but then here we are not ignoring left and right. We are going to the left to work to the right, both sides, right? So whenever, so this is for binary, right? Binary search, it will be either left or either right, not going to both. So if I go to merge sort, let's go to merge sort. So this is merge sort. Say if this is merge sort, and say if this is so if this is say 7 merge sort. So if this is my merge sort, and then either if I go to so my either I may go to my left or we go to right. No, here there is no or. It will be both. Although we'll half, we'll go both to the left and to the right as well. And then uh, Merge sort tree. This is going to be some. Oh, we do merge and then we do again sort. We first is we sort and then when we merge, we kind of. So first is we divide the array into two halves and then we merge it to one, right? So hence that merging is going to take in because we are going to visit all the elements again. Also the yeah. Yeah, so only difference between a binary and a merge sort is basically they are both halving. But then in binary search only one half is kept. Yeah, we need only one call. Either it is going to be the left or either it is going to be the right. The linear work is when you are going to merge it again, right? Is what that. Yeah, I guess. Yeah, binary search is like pruning, like you're cutting the half. Merge sort you are halving, but you are solving for both the sides. Like we are not ignoring any half. So if in the merge sort you just put an if, it can. Yeah, I guess. Merge sort we are going to visit both the halves. So is the left and the right. Although the input size is halved. Also, when you are searching, basically you are saying how many elements are we visiting. If it's an element of size 7, first, if it's a size 7, then in the next it is going to be of size 4. So you see that half relation has come into place. Let's draw the recursive tree for if it's a so suppose it's n, right? So then I'm going to have two halves, say 4 and yeah, either so if it's a 16 size array, so I'm going to equally split into two sides. The middle element is the one, so one is going to have half and the remaining half is going to have the other half, right? But at one point I'm not going to visit the entire half. Like either I'm going to go down this or going down this path. That either condition is what. I see what he's trying to say. Now the main thing is basically to identify when to use recursive. So like when should we when do we go for, remember recursion is again just a form of control flow, right? So either we can do recursive or we can use for, because both are for control flow. But then some, now when should be my go-to approach should be recursive, right? When, because the first thing is when we have a sub problem to solve. This is one and the one of the biggest hints that one could get, right, while solving whether to go for recursion or this is whether do I have a sub problem that I'm solving. For example, if you see your tree, uh, so this is my tree, right? Now what I can say is this is one tree. Now this is another tree. Like this is like a sub tree of this tree, right? If I whatever code I apply here, if I just apply it on the sub parts of it, I'll be able to solve the issue, right? So basically, whenever we have this sub problem kind of thing, our go-to approach is going to be recursive. And one of the biggest examples of doing recursion is it's like one when intuitively when we should go is basically when we are dealing with tree, right? Tree data structure, because it is naturally occurring recursion, right? You have a problem and you have a sub problem. You have a problem, so for example, you have a tree and then you have the sub tree. So whatever you apply to the tree, if you apply to the sub tree, you'll be able to find that. And then again, when you have graphs, right? It's almost, this is very intuitive, right? Whenever you're dealing with a true or graph problem, this comes very intuitive, because inherently trees are made up of subtrees, right? Trees have subtrees in them. Similarly, graph, you have a graph and then you have a subgraph, right? So if you apply it for one part of the graph, the same solution can be used for the remaining part, right? It's very intuitive in nature. So whenever you have that kind of thing, our preferable option is to go for recursion, right? So whenever we have that tree sub tree, it's very intuitively that you already have a sub. Let me arrange the screen a little bit. I guess it's too big to fit in. Wait. Let's select this. Let's have the size change. Is this sidebar is taking some space, right? Let's, yeah. So whenever you have a graph, intuitively they are tree based. So if I zoom it to 100, yeah, just make sure. I'll just write it again. So whenever graphs are inherently tree based, so if it's a, so trees, graphs, these are by natural recursive. By nature, these are recursive in nature. So we don't have to worry about what is going to happen, because If it's they are inherently recursive, then it's a advantage, right? Now the other thing that we need to for example, some other data structure, are we having a sub problem, and will that sub problem be applied to all of the smaller cases, is what we need to think, whether to go to recursive conditional flow or when we are going towards loop. And the way to analyze the recursive is basically how to like tree the recursive diagram or recursive tree nodes is the best way to identify. So you can say, sorry, I don't understand. Why did Siri activate? Something is getting clipped. Oh, it's on this side. Yeah, so whenever basically you have uh is this coming? Oh, let's drag it down. I guess this should be, yeah. So the best way to analyze recursion is basically to use the recursive tree, right? Like how many nodes are we, and the hint to search is number of nodes. How many so number of nodes are basically what are going to represent in my recursive calls. Basically we need to calculate or we need to count how many recursive calls are we making. The moment we have that, uh, recursion is solved. Okay, let's try some questions. So okay, let's try some quiz and let's see how we do. Okay, now which of the following statements is true about grow? Okay, let's, yeah, so there is a loop, right? uh oh, this is pretty similar. This is going to lie till end, so this is a linear n times loop. Now this is inner loop is always multiplied, right? For each iteration this inner is going to be 2. It's incrementing in the power of 2, but that's okay. Okay, let's, let's go to the next. Oh, now this is something, for one n iteration this is going to be, yeah. So if I do half into, this is going to be like j square is less than n. So if I do this is this is already to the power half. But I is incrementing power of 3, right? Hmm. There is no halving happening, but for each iteration of one, the other is in row 10, right? This is very easy. Obviously, I'm halving the input, but now this is okay. So this is going to run basically, and oh, but this is oh yeah. Let me check this thing. So there is a this is cool. So if I have this loop and then I'm going to do 3 times. What's the complexity here? Say if I say n is say n is 1. N is 1 is not a good condition. Let's say n is 5. The first is going to be 1. Then this is going to be I into 3, right? This is 3 is less than n? Yes. There's no halving happening here. Oh, although it is yeah, I guess what is going to happen here is this is yeah, this is controlling the loop, right? So it's going to be yeah, it can be said I into 3 is n, right? And then when you do I, this is going to be log 3 base n. Yeah. It's pretty straightforward if it's halving. If it's n by 2, then it's directly log 2 base n, right? If it's a n is uh if I'm directly halving the input, then it's pretty straightforward. The thing is that condition needs to be true, right? If that condition is false, while condition is false, oh yeah, this is a tricky one. So basically, is having there is a for loop that is running for I less than n times. Increment is 1, and then I have a while loop inside. So this while loop will work only when this condition is true, right? Else it won't work. So we can say this is going to be order of 1. Uh, then you have I less. Oh no, this is should I instead of The outer is going to run one intuition of that is when I'm halving. uh And the other one is, suppose this I have this condition while, and then I'm incrementing in steps of 3, sorry, in multiples of 3. So this is, say n is 5. First going to be 1. I need to count that iteration, right? How many times am I iterating? When n is 5, first is, and my eyes say 1. First is going to be 1. Then it is going to get 3. And then it's going to get, so 9 is going to fail out. So for 5, I ran it 2 times. What if I increase my input size? Let's say I have 10. So first I'm going to do 1, 3, and then 9, right? Then suppose if I have input size as, this is 1, 3, 9, or 12, again this is going to be, but this series is 3 power n series. No, there should be some way. So what if n is 27, then it is going to run Oh, so this condition is what is going to break out the loop, right? Also, in other words, what is happening is this I itself is replacing this. So you can say this is like I power I into, or you can say this as, so this is basically I into 3 is less than n, right? And then this 3 goes over here. So whenever you get that n by 3 thing is basically, No, no, wait. There is how is k base 2n? So even halving or doubling, why? So it's very straightforward when you are halving, right? When you're doubling. Okay, this is something interesting. If it's halving or if it's dividing by 3, it's pretty easy to understand. So there are two graphs. One is reducing, and one is increasing. So what he's trying to say is, yeah. So when we do I into 2, I is I into 2, we say that it's, oh, this is like studying a little bit of graph. There is that decay, and then there is that. Sorry. But how do we get to log n in both? Is what. Oh, so this is something interesting. Okay, so suppose if I'm doing I into 2, right? If I'm doing this approach, so then what is going to happen is I is going to be 2 power 0, 2 power 1, 2 power 2. This is 2 power something, right? So I need to break this. If I say comparing it with n, so now you apply log. So if I say log, so this is basically log 2, right? If you need to convert it into power. So the moment I apply log 2, this k minus 1 comes out, right? Taking log 2 on both sides, okay. Oh, so if it's log 2, then this is and then taking log on both sides. So this k minus 1 is going to be, because log, oh wait, I, this is not right. This is log 2 2 to the power k minus 1, right? This is going to be 1 because this is going to shift here. So anyways, so only thing I'm going to lift with is this. It's mathematically same, but this is something else, remember. And then when I do that halving, so this is going to be n, then this is going to be n by 2 power something, right? So this is going to be 2 power k minus 1. So if I come back here, so I'm going to do n power, uh, if this is going to be my condition, so if I say this is 1, so then I can take it over there. So this is going to be, oh, it ultimately comes to this situation only. So they are doubling up with their halving, that is, okay. Like what is, I guess it's how graphs are drawn, I feel. Like what affects the graph? So when I have a graph, like what will be affecting my graph? Like what operations affect growth? Oh, so there's something called as exponential decay, and also what is going to happen is you are saying that it's increasing by that log 2 rate. Oh, I see what it's trying to say. And that graph will be coming down, but it's just in the opposite direction. Or exponential increase. Also, the technicality behind is that it's increasing by log 2n. Uh, I guess, yeah, that's what it's trying to say. Yeah, so basically we are related with growth, right? So exponential increase will be this way. This is going to, but then again, we are going to say this is going to increase by log 2. And if it's a decrease, so it's going to be this. So even this is a decrease by log 2. Oh, that is an increase, this is a decrease. Ah, okay, yeah, I guess that is all. So basically, we are related with growth whenever we are dealing with loops. Even though it comes out to be the same, but the technical understanding is that one is uh, decreasing by log 2n and one is increasing by log 2n. Okay, yeah, so um that is all for this. I hope you guys liked it, and I'll see you guys in the next one. Till that time, take care. Bye bye.